Right, so far we looked at moving the drone in X, Y and Z height, and you can probably see that it works quite nicely doing that. Now the next thing we need to look at is when we need to store some data from this so as we can actually plot as a graph the X motion against time. So we might have, say, a graph of, say, height against time, so we can get some sort of graph where it changes height, and we can do that. We can also do this against, say, X or Y as well, and then we could possibly, even if we've got X, Y and Z, we could do a 3D plot, sort of X, Y and height. And Matlab has facilities now for plotting these type of graphs and these 3D graphs as well. This is using a command called plot. We do plot H, T, plot height against time, and this one we do plot 3 X, Y, H. So using plot 3 we could plot a 3D plot. So these are nice facilities now within Matlab for producing graphs of the variable against time, and these are good things to go in your report. Otherwise you've just got the fact you've got a video of the drone moving around, but you've got no hard graphs. So we need graphs of these type to make sense of what we're doing, really. So this is fairly straightforward, but not 100% straightforward. Let me try and explain some of the concepts behind this for you. And the first thing I want to talk about is just how we go about plotting data in Matlab. That's a standard way of plotting data in Matlab, which we use throughout the project and everyone uses for doing Matlab as well. And let's say we have to plot some data, and the data is always in the form of an array or a vector. So these are data structures which look like this. And I haven't got the board quite dry enough. So these are data structures that look like this. This would be an array, or like this if it's a vector. Let's try a bit board. Dry enough. So we need to define how to make these data structures in Matlab and then how to plot them. So this part is quite easy. I'm just getting some different pens. We'll discuss this first of all from the point of view of Matlab data structures, and then we can apply it to the drone a little bit later on. So let's say now we want to define an array. So we can put T equals open square brackets. Then we can put some numbers in here. So let's say 0, 1, 2, 3, 4, 5, close square brackets. Now there's spaces in here. You could put commas as well, but spaces is quicker than commas. And this could define, this is called an array, and it's called T. We could have another one called, say, H. That could be, say, 2, 4, 0, say 2, 4, 16, 32, 64, 128. Now notice I've made these two the same length. This has got 6 numbers in, it's got 1, 2, 3, 4. They have to be the same length, these two. arrays, and then we can use plot t, h. So if we type those 3 lines of code now into Matlab, it would plot a graph of t against h for us. So we'd get a graph which went from 0 to 5, and this would go from 0 to 128, and we'd have some points there, and it would join the points up with a graph that go 0 to 5, that 0 to 128. So that's the first little idea now behind plotting graphs. Okay, so that's the first little thing, thinking. And you go and practice this, and then that gives you an idea of how these data structures work, and how you can use this like plot command to plot out a graph. Now let's see what else we could do. The next thing we need to do is have a bit more control over the data structures. So for instance now, let's say we wanted T to be an array. I don't have much luck with my pens today. So you want it to be T, to be an array going 0, say 0.1, 0.2, 0.3, all the way up to say 100. So we could type in all these numbers now. There'd probably be about 1,001 of them, wouldn't there? So we could type in 1,001 numbers, but that could be quite annoying to do. So we could have a special command in Matlab now, which is the t equals open square brackets 0 and a colon 0.1. This is the step length. This is the first value, and this is the final value. So we're going to make t, this is the first value. This is the step, and this is the final value. And that will then generate that array for us. And so this is another little thing we can do in Matlab now to generate large arrays quickly with fixed steps in. So this is another little thing to think about, to generate these arrays for different purposes. And there's one more concept that we need to have. And then we've got all the ideas to do all the main tricks in the project. Say we've got x equal to say 0, 1, 2, 3, and y equals, let's say, 2, 4, 6, 8. Now say we wanted to add x to y. So in Matlab, it's got a command, say z equals x plus y. And it would then add that number to that number, that number to that one, that one to that one, that one to that one. So that would be a quick way of doing it. But there's another way of doing it, which is a bit slower, but it's a sort of method that we deploy in our calculations. And this is using that something called a for loop. So we have a piece of code now said that for n, say, equals 1, step 1, 2, and it's going to do it 1, 2, 3, 4 times. So this is a loop now, this is called a for loop, and for every for loop we have to have a command called end. So when the for loop gets to this line here, it goes around this loop, and it'll go around it for n equals 1 with a step of 1 to 4. So it's going to go around this with n equals 1, n equals 2, n equals 3, n equals 4. If this was say 0.1 in here, Then it would start at 1, then it go to 1.1, 1.2, 1.3, 1.4, 1.5, all the way up to 4. So you've got some control of this is the first value, this is the final value, this is the step. We'll stick it to 1 for the moment, just to make it simple. Now, this element here is the element 1, 1. So in terms of, this is the element here, 1, 1. This is the element 1, 2. That's the element 1, 3. And this is the element 1, 4. This is how you can sort of define it using like a data structure. So you go with a data structure, you go that way first and that way second. So if it's somewhere down here, it'll be say N and M across. So that's how we define. It's like a stack like you do in standard matrix calculations. So this is the element 1 that way, 1 in. This is the element 1 that way, 2 in. This is the element 1 in, 3, and that's 1 in 4. So we could have a bit of code now. So for N equals 1, step 1 to 4, and we could put say H, for instance, equal to X, open round bracket this time, 1 comma N plus Y, 1 comma N. That would have to be a bit more complicated now. H, 1, N. So what will happen now is it'll make say N starts off as 1, so H11 is X11 plus Y11. So if that's X11, this is Y1, so it adds that one to that one and puts in H11. And it does it then for, because it's got a loop here, it's looping around here. And so it does this 4 times, and it'll add then this to this. And this idea of using a loop here and incrementing an array is another useful feature that we have to have for sorting out how the drone data can be collected and plotted. So those are the first 2 little ideas. One is using arrays. We could use vectors as well. In vectors, then you'd have that number and that number as number n. And this would become a 1, because vectors go that way, n down that way, 1 that way, whereas arrays go 1 that way and n that way. Now let's see what else we could look at. That's probably a good start. So let's look at some Matlab programs now that do this type of thing, and just familiarise yourself with this concept. So you'll need this concept for sorting out the data from the drone. So we'll now move on to a little Matlab program, or set of programs, demonstrating some of these concepts. And then what we're going to do is we're going to use these ideas then to understand how to take data from the drone and plot it as graphs. So here's our first little demonstration. We've got t equals 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 10. So actually 11 elements there. And then I put some values for y here. And I've made sure that t is the same length as y. And then I've also made, I'll make z equal to y, but I'm not using this particular line. Let's take that line out for a moment. And it's doing a plot t comma y. So it's going to plot t against y. That's plotting 2 arrays. So if I run the program, and here's the graph of t that way, 0 to 10, and y going this way. And it automatically scales it for you. If we introduce a third variable, let's say we make z equal to 2 times, I can find times on my keyboard, 2 times y, and I can now if you want to take a line of code out, you have a % sign in front of it. It stops that code from running, and I'll bring this other piece of code in, which is called plot3 now, and you have to give it 3 variables, t, z and y, so it'll now plot these as a 3D plot. So if I run that one, we now get a 3D plot, and this is interesting because you can move it around to see in the different directions how it looks. This is a 3D plot now. And this could be handy for plotting out 3D movements of your drone. So there's a couple of commands now, plot and plot3, that we can use for plotting graphs. So here's another example now. This time I've got same t, but y now I've made using a command called zeros 1, 11. This makes an array the same size. This has got 11 elements in. Makes it an array of size 1 by 11 full of noughts. Handy just to set up a data structure. And here I'm using a for loop now, so it's going for n equals 1, step 1 to 11, because there's 11 elements in the array. And it's saying that y, 1n, is 2 times the t value plus 3 times t squared. So it's like a graph, 2t plus 3t squared. And then it's running around this loop 11 times, filling up this array with values for y, and then it's able to plot them out for me. So if I run this now, there's the graph of this time a function, a 2t plus 3t squared. If I want to make it into a cubic, I could put times, say, t brackets 1, n, and I've made it into a cubic equation, 2t plus 3t cubed, which would be a different graph. Don't know what it'll look like. It doesn't look much different, does it? But it's probably bigger numbers up here this time. So there's an example now of using a for loop to manipulate an array and then plot it out. So have a practice at some of these, and it'll be handy when we come to look at the code that we're using. Right, here's another way of doing it. It's the same code, the same problem, but this time we're solving it using a while loop. So the basic problem is the same. We've got the definition of t, definition of y, and then we put an extra piece of line in here, n equals 1. This is the first value we're going to use for n in our problem, which is the first value here, 1, because that's 1, that's 2, that's 3. Now, this is while n is less than or equal to 11. So if n is less than or equal to 11, it's going to run this code. But as soon as it gets bigger than 11, it stops. That's how a while loop works. But within a while loop, you also need to move n on. So we start off with n is 1. The first time around is 1, but then this makes n equals n plus 1, so it becomes 2. So the second time it's 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10, then 11. Then it gets to 12, it stops. And so this line is the same. We've put x and n equals 1 in there, incremented n in there, and got it on a while loop. So if we run this program, it'll give us exactly the same answer as what we had before. It gives us exactly the same graph. So this is now another data structure that we use within the program, a while loop, based on some values. Can be different values here. They can either be numbers in an array, but what we're going to make use of is time within the program. So we're going to use time to control what's going on around here. So that's the third thing to understand, is this while loop. So we can use a for loop or a while loop to manipulate these arrays. Now the graphs we're going to want to do will have to run in real time. So we'll need to use the onboard Matlab timer. This is an explanation of how this works. There are two commands, tick and tock. So tick starts the timer and tock is the current value of the timer since you started it. So it's like a stopwatch. Tick starts it off. If you look at it at a particular point in time, that value is called tock, tick tock. So I've put A equal to tick. So that means the variable A now is associated with a timer. And then I've put a little for loop in here, and it runs this loop 10,000 times, adding a number. So it's just something to give it something to do. And then when it's done that, it then sees how long it took by using the tock value of A. So if we run this now, and it's taken 0.6 of a second to do it. So that one, if you run it again, it's taken about 0.61, so it's never quite the same because the computer's doing, like this time it's taken 0.69, this time 0.7. It seems to be taking longer every time, doesn't it? 0.78, this time back to 0.56. So you can see to go through this code, that's because the computer itself is doing other things. It's like checking if I've got any emails. So whilst it's doing that, it hasn't got time to count these numbers because it can only do one thing at a time. Now, one interesting thing about Matlab is if you put a the reason this is so slow is because it's printing the numbers onto the screen here. So if you put a semicolon behind the thing, it stops it from printing onto the screen, and that'll speed up your code no end. So it's the same code now with a semicolon here, so it doesn't print this number onto the screen, which is what it did before. If you look, it printed all the numbers out here, all different values of n as it counted up. So this time we're not going to stop it from counting with a semicolon at the end. But run the code again now, you'll see this time smashes right down to next to no time at all. This time 1 millisecond. So it took a millisecond. If you put an extra two noughts in here now, so it's going to count up to, let's see, 1, 2, 3, to 1,000,000. Let's see how long that takes the Matlab to count to 1,000,000. So it would take you 36 days to do this. Let's see how quickly Matlab can do it. It's done it in 0.005, 5 milliseconds, what takes you 36 days. But you can see how quick Matlab is. If we took the semicolon out, this would probably take about, printing to the screen to 1,000,000, would probably take about 2 or 3 minutes. So this is the tick and the tock. I just wanted to mention that because we use that to get real-time data from the drone as well. Okay, so here's the application of some of that stuff now to the Tello, so as we can try and see if we can plot a graph of height against time. So first command we've got is try clear all, r equals rise and takeoff. So there's our standard piece of code, and the bottom we've got the bit of code that catches if it goes wrong. It could go wrong in this, so it's handy to have this code in. So there's our main code. And then I'm putting n equals 1. This is going to be an array number. The first number in the array is going to be 1. I'm going to use a value for time, and this is going to start off with t as 0. When you run a computer program, it's got to know what the first value is. So t is for time, and its initial value is 0. And then this variable t run now is tick. So this is going to set off a timer now associated with t run. If we do a tock against t run, we can see what the current time is. So that's a bit of the timer there. I've then done a move up command. So it's moving up the rise a distance of 1 meter, and wait until done is now false. This means now that whilst it's doing this command, it can run other Matlab code as well. So this is the Matlab code now that we have to have
to do the data logging. So it's while TOC of trun is less than 10. So trun is tick, so it starts it off. So this is going to do this particular loop here for 10 seconds. So it's going to run round this loop that's between there and there for 10 seconds. So it's quite easy. TOC of trun is less than 10. If you wanted for 100 seconds, you'd make that 100. Then uses another timer now called TS. So once it gets into this loop here now, it puts TS equal to tick. So TS is also a separate timer to trun. So we've got two stopwatches. One stopwatch is run for 10 seconds, and TS now is seeing how long it takes to collect some data in. So we've got a command now called read speed. Now this one reads the speed of the Tello drone in height, and read height measures the height, and so they get assigned to speed and height. Now the next command is a bit tricky, and for a long time the thing didn't work, but I had to get in touch with Matlab Central, and they gave me this little line of code here. Now what happens is sometimes the drone doesn't send data back. Say it's sending back about 1,000 points per data, but one of those data points might get wrong, just get corrupted. So what this line does is it just checks that the data being sent back is okay. And once I put this line in, everything worked. So you could try it without this line and without this end, and it would work sometimes, but sometimes it wouldn't work. So it's a trick that guarantees it works. You have to worry about it too much. So it then puts, remember the n was 1, so it puts h of 1. Now h is an array we're using to control the height values, and it puts equal to height, which is what it's just read from the drone here. And then it puts the time step, that's how long it's taken to do that, is TOC of TS. So remember, tick started off, so TOC. So this is going to be, time step's going to be quite small. It's the time it's taken to take one reading from the drone and put it into the array. And then we can say that the total time is the current time plus t step, because it's just measured how long it's taken to do this particular step. So the total time is the current time plus t step, and the next time round the value for t will be this one, so then it'll add an extra time step in. And then it's writing then this value of t into an array called t, and then it's incrementing n by 1, so it's got the next number of the array to come in. So all the things I've talked about in the previous thing now are in this code. And then once this is run now for 10 seconds, it runs around here for 10 seconds. When it comes out, it lands the drone and then plots time against height, and then we'll get the graph of time against height. So just to go through it again, this is a sort of standard program that we have. Puts n as 1, puts t as 0, and trun equals tick. So trun now is a timer, and it started, and it uses the TOC of trun against the time 10 seconds here, so it runs this particular while loop for 10 seconds, so we can control how long the time it stays in this loop for by changing that number there. Then uses a separate timer called TS to time how long it takes to go around this loop once. So once it's gone around the loop once, the value of time gets incremented by that time step. And so you keep on adding the time step on and moving on in time. So that's what that line does there. And the t-step TOC takes the time it takes to do this bit of code here. It takes a bit of time, this, because you've got to read the data from the drone and then write it into an array. That's what's going to take a bit of time. So we've got two commands for reading the speed. We can read the speed and we can also read the height. Assign those to some variables. You can call them what you like, but height and speed and height seems quite sensible. This is a line of code which is dubious really, but it has to be there. This is in case you get a data error in coming back from the drone. The trouble is if you get data error, the program crashes and it stops. So this stops the program from crashing. So it then assigns, then having read the height using this read height command, it assigns it to an array h. This is the array we're going to plot, and then every time it goes around this loop it has to move the array one on, like 1, 2, 3, 4, 5. So we've got different values to plot out. The time step that was taken to do that is the toc of ts, then increments the time, puts the value of time into the array so it can plot t against h at some subsequent time, and then increments n on by 1. So next time we go around this, it sticks into the next element in the array. So that's the code. So we run that code, then it lands the drone, and then it plots t against h. So let's have a look at that going on now. I'll get the drone, we'll run the code, we'll get the drone to take off, and we can plot the t against height. Right, so you've got the program running now. I've also got my camera working, so as I can watch the little drone down here. It's going to take off, hover at about a meter, half a meter, go up to a meter, store the data, and then land back down. So that's what we're expecting to see. So if we run this now and go on to, it's a bit slow, just hovering. So now it's going to go up to about a meter, so up it goes, collecting data as it goes up, just about gets within inside the screen, and then it'll land after 10 seconds. When it comes after 10 seconds, it lands. So there's our drone doing the job, and if we have a look now, this is the graph that we got off the drone. So it was starting off at a certain height, about 0.3 of a meter, and then it went up 1 meter, so it ended up at 1.3 meters. And this is the graph now of height against time. So it's a bit disappointing really, because it's not a nice smooth graph, is it? It's not a nice smooth graph, which is a bit of a nuisance really. We'd like a nice sort of smooth graph there. So we need to find some way now of possibly modifying this graph so it's a nice smooth line of changing height against time. This is height against time. So let's have a look how we could do that. Just before we do that though, let's go back to this program. If we change this variable here from height to speed, we could actually plot the speed of the drone as it went about its business. So if we just change this to momentarily to speed, if you spell it right, it helps. So we're now going to plot the height, the speed of the drone, as opposed to the height of the drone. So I'm just going to put a little bit of code in here. Here. That'll pause through. That'll just give me enough time for the program for me to switch from the Matlab mode into the camera mode. So run this now and then go to camera. Here we go. It just takes about 3 seconds. It's going hovering, and up it goes. And I didn't do it at all then. It crashed out. Didn't like that. So that was not such a good one. That I just pause that. Okay, so now I've changed it to speed. But one of the things about speed is it actually measures speed in X, Y, and Z. So speed 1, open brackets 1 here, is the X speed. Speed 2 is the Y speed. And speed 3 is the height speed. So I've had to put a speed 3 in there. I've also to put a comma 1 in there and a comma 1 in there to make the data structures compatible. It's a bit annoying, but that's how it works. So let's have a look at this now. We can now plot speed of the drone as it took off and went up to height. So if we run this, here's the drone in again. So it hovers, and then it goes. So this is the bit that we're data logging now. So we're data logging as it moves up, measuring its speed, and then as it stops there for 10 seconds, comes down and lands. So let's have a look now what we got. And this time, stop being very nice with me. Index exceeds the number of array elements. Oh well, it didn't work. It should have worked though. Let's try it again. Okay, so run out of memory. If it runs out of memory, type in clear the Matlab command prompt, and that will release memory in case something's going wrong. So just click there, clear, and then if we click on run here, go to the camera, it should run. Here it goes. It's moving about a bit every time I take a picture. Never mind. Up it goes. It should be data logging as it goes up there. So it runs for 10 seconds, just gets that shot, comes back down, gets tangled up in the carpet. No worries about that. And it's done it again. This is a nuisance. I've slightly cheated here, but this is the graph now that we get of speed against time. So I'll get this graph here. This is the graph of speed. Again, notice it comes over in this sort of quantized form, which is a little bit disappointing really. But one thing we could do, if we integrate speed, you can get height. So if we work out the area underneath this curve as it's going along, so work out the area underneath this curve as it's going along, that should be an indication of height. So if we integrate speed, we'll get height. Notice these numbers are going negative in this particular sense now, because remember, generally for the drone, positive is down and negative is up. So because it's going up, it's negative speed. That's sort of back to front thinking about height in a like dynamics context. Anyway, that's the speed. So we're going to have another last trick now, is to work out the area underneath this graph as we're going along, and that might give us a nicer looking graph at least of speed by integrating this space under here to get an estimation for the height. Right, so in this case now we're going to add a little bit of code to it. The speed comes back as 3 things, and it's so we have to use an n by 1 array here, make this an n by 1 as well. So, but we could have speed 1, speed 2 and speed 3 there. Speed 1 is x, speed 2 is y, speed 3 is z. It's also negative up, positive down. And there's a bit of code here now. This works out the length of t once you've got your overall plot that tells how long the array is. This makes an estimate of the height the same size, and then we have a for loop here then, and this uses an Euler integration technique to work out the estimated height from the speed. So this is the speed here, and it integrates the speed and then gets that signal and then plots out the time against the estimated height, which should be a nice smoother signal. So let's run the drone now. Go to my camera. Okay, just leveling off, and if it goes, 2 seconds, there we go. When I get close to my light, then come down a second. And come down, and then it runs, Now we give a graph which is crashed out, which is very nice of it. Let's just try this once more, shall we? Here we go. Get onto the. There it goes. Doesn't always work. Just do it most of the time. Goes up to the right height. Wait for 10 seconds. And comes down and get the land. Okay. And then when it's getting finished, there's the graph now. And it's gone, hasn't gone quite to a metre this time. It's gone a bit light of a metre. So we could have adjusted that by the number in here, the 1.3. We'd made that a 1.4 for instance, so it's not perfect this. If that had been 1.4, we'd have probably got a better signal. We just copy this bit of code into the Matlab command line and run it. There we are, I think by changing to 1.4 we've got a more, it's gone to 1. So it's not a perfect method this, but it's within 5% and it's giving a nicer graph now of height against time. It looks more like acceptable than this staircase thing that we had before. And the other thing that's interesting about this now is that the drone itself doesn't have, although it has a height sensor, can measure height, it can't measure x and y, which is disappointing, but you can measure speed in x and y. So if we use this trick of integration, then we can make estimates of x and y, which are quite good, and then we can get an x, y and z motion of the drone. So let me try and show you that next. Now this next program is, we're going to spend a bit, this is as far as I want you to go for the moment, is to understand this. I just want to sort of give you a taster for what we could do next. We could do the same as we've got here, but what I've done is I've done 3 motions rather than 1, so I've got this code 3 times for move up, move forwards, move up and move left, and I've put all the numbers. I've got, this time I'll have speed 1, 2 and 3 here, and I'll have 3 estimates, x, y and z estimates, and we can use a plot 3 then to plot the 3-dimensional motion of the drone. So that's the little program I've got here. So we're not going to go through this program today. This will be the next video. But this one you can just basically see it's picking up speed 1, speed 2 and speed 3 there. That's the difference. And then it's doing some maneuvers. So it's doing a move up, it's moving a move left, and before that it moved a move forward, then a move up, and then a move left, and then it worked out the estimates for x, y and z, and then I've used a plot 3 then to plot an x, y, z 3-dimensional plot of the drone moving. So this is quite a nice way of describing how the drone works. You could also have some other code here plotting t against x and t against y and t against h, so you could get individual x, y, z transient responses as well, but we can't have all things at the same time, so we're going to go for plot 3 in this particular case. So we're going to run this program now just as for you to see it work. So here it goes, hovering, it's going to move towards me now. Come on, move towards me, here it goes, move towards me, move back, move to there, stop, then move up, move up, move up, keep the up now, right down left, I can put those in the door, and now it's good to land. Didn't do the move up for some reason, and that's its motion. You see, it didn't do the move up for some reason. It moved and then went left, didn't it? Shouldn't have done that. Let's have one more go at this. You've never done that for me before. Disappointing little thing. I'm just going to have to move it. We'll take a second. Once I'm back again, let's have another go at this. So I run the program.
Okay. There's a confidence if you can move forward. There. Now move up. There you go. And then move to the left if it's our right. And correct. And then it lands. There you go. And you can pull that quickly. I'll get a graph. There's the move forward, there's the move up, and there's the move left. So you can see now, this is quite a handy graph, and you can move this graph around in this 3D space as well. See how it moved in, you can look at its like transient responses in different directions. So it's quite a smart little program, this, isn't it? And last thing I'm going to do is, if I hit the drone with my hand, I can make it wobble off this path. So you can then see the effect of me pushing the drone on the overall transient. It's not going to be quite as smooth as this, because it moves quite smoothly, doesn't it, the drone? It doesn't sort of deviate much from its desired trajectory. So I'm going to go in and interfere with it and get it to move a bit off its trajectory, so you can see that happening. So again, I'm going to have to move the drone . So I have to be fast now. I'm just going to put, to give us a bit of time, I'm going to put a pause 3 here. That'll give me 3 seconds to run the program and get the video on. So here we go. Give me 3 seconds. There we go, so it's going to be fast. So this time you can see now, as I gave it a little bash as it went along, it didn't quite go in that straight line that we're expecting. So you can see it does a real time response. I didn't bash it enough here, did I? I bashed it a bit there though, and it went off target then came back in. So that's another graph. Now you can see how it behaved, and you can see this is a real time 3D plot, and if it does something weird, it'll plot it out in 3D for you. If we want to look at the individual X, Y, Z commands, we could use the plot. So we're looking at X motion. We could get this graph here, copy that code, and paste it into the command line and run it. And there's the graph of how it changed its X position. If I wanted it for Y, I could just change that to Y or Z. Let's try. I do that. My cursor on there. Do that, and then change this to Z. And that's how it sort of changed height. It's quite a nice transient, really, wasn't it? Changed. I think it was meant to be 0.5 meter, so it wasn't perfect. But gives you some idea now about how we can use the program to track the drone in X, Y, Z, and plot it out in X, Y, Z, or plot it out as X and Y and Z against time individually. And we can go through this program again in more detail, but it's basically just an extension of the one we've looked at. And the only thing that we could add to this now would be where we could make the drone yaw as well. So if we take yaw into account as well, so we could like yaw the drone, that would give us a slightly different set of mathematics. We'd have to use causes and sines to work out where it moved in X, Y, or X and Z anyway. X and Y. The Z isn't affected by the yaw, but clearly the X and Y are affected by the yaw. So we could add yaw and some slightly modified X and Y coordinates therefore in the future. That could be another thing we could do, and then we'd have a nice set of programs which we could run
make the drone do different mission profiles, and also plot out reasonably accurately what it did during that transient response.